section 8.2. We're talking about union, intersection, complement, and odds. So we're talking about this all in the context of union, intersection, complement in terms of probabilities. Now the book goes in and talks about, what exactly is the union of an event or an intersection of an event or a complement. I'd just like to remind us, events are sets, and specifically they're sets inside the universal, inside the sample space, which is our universal set. Okay. So when I talk about the union, intersection, complement of events, just think of sets. Great. So first let's talk about union and intersection. Now, the easiest way, and this is only useful if the sample spaces we're looking at are pretty small, of computing the probability of a union or intersection is just directly counting. But the most important thing here is for us to be able to, we need to be able to interpret a problem and determine whether it's an intersection or a union. And also to figure out which counting technique to use. But at first we're just going to do something simple. So our first example, we're going to flip a coin three times, and so our sample space looks like this. I could get heads, 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 then heads, heads, tails, then heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. That should be one. Just put a enter right there. That's 8 things. So let's just notice that the number of things inside of S is 8. Okay. Let's ask a couple of questions. Okay, what is the probability that the first flip is heads and heads comes up twice? Okay. Well, when I see the word and, this typically means an intersection. We've been talking a lot about the word and meaning multiplication, but in this context it's going to mean intersection. The reason being, it's not like we're making two choices. It's heads coming up first and coming up twice. Anyways, well, let's look at the ways that this can happen. Well, heads coming up first, let's call that F. This could be heads, 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 tails, heads, tails, heads, or heads, tails, tails. That's the ways that it can come up first. How many ways can it come up twice? It could be heads, heads, tails, heads, tails, heads, or tails, heads, heads. Now, we're looking for the intersection of these because we're looking for both of these happening. So the probability of F and T is the probability of F, and since I haven't set up things, I'm going to use the letter N to mean intersection because it kind of looks like the intersection. F intersect T, which is, well, what is it? What is F intersect T? It's these first two guys which actually have heads as the first flip. They're right here and here. So that's heads, heads, tails, and heads, tails, heads. And the important thing, and then since we're assuming equally likely outcomes, which we typically do when we're looking at something random like this, is the number of ways of getting heads first and 2 heads divided by the number of things in our sample space, which is 2 divided by 8, which is 1/4. Great. So here we're just doing things literally by counting. Now, let's say, what is the probability that the first or the last flip is heads? And here, again, I'm using the mathematicians, or, which is or both. So again, the first, the way forward has come up first is heads, 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 tails, heads, or heads, heads, tails, or heads, tails, tails. The number of ways for it to come up last are HHH, HTH, THH, or TDH. Okay, now we're looking for a union here. We're looking for one or the other or both, so that's a union. So when I put them together, I have heads, 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 tails, heads. Those are the two that they share. First has these two guys in it, and last has these two guys in it. So altogether, we have that the probability of F or L, first or last, is the probability of F union L, which is the probability of, which is the number of ways that FUL happens divided by the number of ways, total things in our sample space, which is going to be, we've got 1, 2, 3, 4, 5, 6. 6 divided by 8 gives us 3/4. Great. Now, when things are larger, we generally want to deal with something other than having to count things out. So we actually have an addition rule that we had for counting, and it works for probability too, which is that the probability of a union, let me write it over here, is equal to the probability of A plus the probability of B minus the probability of the intersection. This looks exactly like what we had before when we had the number of things in each set as opposed to the probability of things. So it comes out exactly the same. We also, so let's do an example of this. I just like to have consistent notation. Let's look at the above thing again. Well, let's again ask, what is the probability of heads first or last or both? Well, this says that to compute it, we could take, again, we could take the probability of first or last is the probability of heads first plus the probability of heads last minus the probability of heads first and last. Let's think about this. We don't even really need to write things out too carefully here. If heads is first, the probability that heads is first, well, we only care about what happens on the first flip. The second two can be anything. So what is the probability of heads on any given flip? 1/2. We know that. So that means that the probability of getting heads on the first flip is 1/2. Similarly, we have that the probability of getting heads on the last flip is 1/2. Now how about the probability of both of them happening, first and last? Well, note here that the middle flip can be anything, so we only care about the first and last flip. Now the possibilities for the first and last flip are heads and heads, heads and tails, tails and heads, and tails and tails. And so there's only one way that we can get heads on the first and last flip. Probability of heads on the first and last flip is 1 out of 4. This one way, out of the 4 possible ways that we get different flips for the first and last. So this tells us that the probability of the union is the probability of first plus the probability of the last minus the probability of the first and the last, which is equal to 1/2 plus 1/2 minus 1/4, which you can check as 3/4. It's the same answer we got before. Now we also saw that things were a lot easier to count if we could assume that the sets were disjoint. Well, remember, all two sets are disjoint if their intersection is the empty set. Let me even write that as just 0. Well, in the context of events, we say two events that are disjoint are, we call them mutually exclusive. That's just the vocabulary that we use in the context of probability. And so what we have is this. If A and B are mutually exclusive events, then the probability of A union B is the probability of A plus the probability of B. We don't have to worry about subtracting off the intersection because the intersection is empty. Okay, so let's do another example using this. Example 3, again flipping a coin 3 times. What is the probability that heads or tails comes up 3 times? Now, these two events are heads, 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 and tails, tails, tails. These are disjoint. These are clearly mutually exclusive. You can't get heads 3 times in a row and tails 3 times in a row if you only flip the coin 3 times. That just doesn't make any sense. Okay, so the probability of heads or tails 3 times is equal to the probability of heads, heads, heads plus the probability of tails, 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 which is the 1 out of 8 possibilities. Remember, there are 8 ways to flip a coin 3 times, and heads, heads, heads is just 1, plus 1 out of 8 ways to get tails 3 times, so you get a quarter. So actually, a quarter of the time that you flip a coin 3 times, you should expect heads or tails to come up all 3 times, the same flip to come up 3 times. I don't know. Interesting. Finally, let's do one example where we're using numbers that aren't coming from the assumption of equally likely things. Let's use some sort of empirical data. So let's suppose that 60% of voters are dissatisfied with Obama's job performance, and 80% are dissatisfied with Congress's performance, and 50% are dissatisfied with both, and that's supposed to say Congress. Then the question is, what is the probability that you're dissatisfied with one or the other? Well, it's the probability that are dissatisfied with Obama plus those who are dissatisfied with Congress minus those who are dissatisfied with both. Now, turning the percents into probabilities, we have that 60% or 0.6 probability are dissatisfied with Obama, plus 80% or 0.8 are dissatisfied with Congress, minus 0.5, 50% are dissatisfied with both. That's 1.4 minus 0.5, which is equal to 0.9. So 90% of voters are dissatisfied with both. Okay. Now there's the last set operation we're going to talk about now are complements. And let's remember that if E is an event or a set or whatever, E prime is the set of all outcomes not in E. Or, you know, it's all the elements that are not in, the given set. Okay, well, we have a nice simple fact here. The probability of a complement is just 1 minus the probability of whatever the event is. This makes intuitive sense. If there's a 10% chance of rain, then there's a 90% chance of no rain. I don't have to tell you that. That seems pretty intuitive. If there's a 0.01% chance of you winning the lottery, there's a 99.99% chance of you losing the lottery. Okay. Great. So let's look at some specific examples of this. So this is example number, it doesn't really matter, but I like to just keep things sort of ordered. 5. This is example number 6, I guess. Did I order these right? I don't care. I don't really care. Example number 6. Sock drawer again. Let's do a variation on the sock drawer problem. So I have 6 white, 5 gray, and 4 black socks unmatched in my drawer. Why 5 gray? I lost one. I pull out 3. What is the probability I pick out a matching pair? Well, this is annoying if we want to do it directly. If we did it directly, we'd have to say, well, I could pull out 3 whites, I could pull out a white, white, and a gray, a white, white, and a black, or I could pull out 3 grays, or gray, gray, white, etc. This is annoying. We have so many different things to consider. But let's look at the complement. The complement of pulling out a matching pair is pulling out one of each color. I have 3 colors, I'm pulling out 3. The only way I'm not going to get a matching pair is if I pull out 3 different colors. So white, green, and black. So that means that the probability of a match is equal to 1 minus the probability of pulling out a white and a gray and a black. So I just have to figure that out. Well, what is the total sample space here? Our sample space is, all ways of choosing 3 socks from 15. And this is a combination because the order I can't repeat, and order doesn't matter. I have the same 3 socks no matter how I pull them out, but I can't pull the same sock out twice because I can't put the same sock on my, both feet. I suppose I could try to squeeze both my feet into a single sock, but no, that would make no sense. That would just make no sense. Okay. So that means that the number of ways I can pull out 3 socks from 15 is 3C15, 15C3, which is 15 factorial divided by 3 factorial times 15 minus 3 factorial. I'll let you compute this out, but it's 455. Great. Now, how many ways can I pull out a white, a gray, and a black? Well, this is just the multiplication principle. Because it's just how many ways can I pull out a white sock? 6. How many times can I pull out a gray sock? 5. How many times can I pull out a black sock? 4. So this is the total number of ways that I can pull out a white and a gray and a black sock. Okay, so this works out to, what, 120. So now what happens then is the probability of pulling out a white, gray, and black is 120 divided by 455, which I've already computed is 24 divided by 65. So that means the probability of a match is 1 minus this probability, which is 41 over 65. This is greater than 1/2, so actually if I just pulled out 3 socks from this drawer, I'd have a pretty good chance of actually pulling out a pair. So, whatever. Okay, the last example I'm going to do here is a classic one called the birthday problem. And the question is this: given a room of people, what is the probability that at least 2 share a birthday? So we're looking for the probability that at least 2 share a birthday. And the complement of this event is that nobody shares a birthday. So the probability that at least 2 share a birthday is 1 minus the probability that nobody shares a birthday. So we want to figure out this second probability. It's going to be a lot easier to figure out than this first probability. Well, what is our sample? We're going to assume that birthdays are evenly distributed throughout the year, and we're going to ignore leap years because that just makes our analysis a little bit more annoying. So this means that anybody has an equal chance. So being born on a given day, the day of your birth, is completely random. It's not really, but and so all outcomes are equally likely. So that means that to count the number of ways that no two share, I have to divide the number of ways that no two people can share a birthday by the number of ways that I can just distribute the number of ways that people can have birthdays. Oh, that was my son briefly. How do you like that? Okay. Well, how many ways can a room of let's say a room of 23 people? Why not? So, what is the samples? How many ways can I? What is the number of ways that I can just distribute the birthdays? Well, the first person has 365 birthdays that they could choose from. The second person could also have any 365 birthdays. It's totally possible that they could have the same birthday. They might not. The third person also has 365 days they could have been born. All the way down to the 23rd person could have 365 birthdays. So that means that the number of ways that we can just distribute birthdays is 365 times itself 23 times. It's that number. That's a big number. Okay. But what is the number of ways that no two people can share their birthdays? Well, this we can really look at as a permutation, but let's look at it this way. The first person can have any of 365 birthdays. But once they choose their birthday, the next person can only have one of any 364. Because because the first one's already been determined. The third person can have any birthday except for what the first and the second have, so they have 363, etc. This is really 365p23 because we are choosing 23 birthdays out of the 365. The order matters because we're putting the people in order and choosing their birthdays, and we can't repeat because that's just the assumption. So this number is whatever. So then the probability that no two share is whatever 365p23 divided by 365 to the 23rd is, and this happens to be equal to about, I guess I can't do a little squiggly equal sign. It's equal to about 0.493. So what this means then is that the probability that at least two share a birthday is 1 minus 0.493, which is equal to 0.507. Interesting. So you only need 23 people in a room for it to be more likely than not that two people share a birthday. Interesting. Now, in our class, we generally have about 30 people. So in a room with 30 people, it turns out the probability that at least two share a birthday is equal to 0.706. That's pretty crazy. So you can ask me in class to have us go around and see if people share, anybody shares a birthday. Most likely it will happen, although in the past I've been jerked over by statistics or probability because, it's not exact, it's just a probability. So about 70.6% of the time, I should astound you, and the other 29.4% of the time, you'll say, hey teacher, well, sucks to be you, whatever. Yeah. Anyways. And